the geographic cone or conus geographus. And so when we started our studies, our goal was to ask the question, why does this snail, which is 3 or 4 inches long, why is it able to kill people? Okay? So that's a straightforward question, and one that you could approach by biochemistry. And so in the Philippines, it's not hard to get conus geographus. There are lots of conus geographus around, and it's not hard to dissect the snails and collect their venom. But if what you're interested in is what component of the venom kills people, it's not entirely obvious what kind of assay you should use, at least an assay that's ethically permissible. And so the assay we did use, and what I'd like to show you, is that this assay is very, very simple. And it's the first equipment we had in our laboratory in the Philippines. So Lourdes Cruz and I started this work. And what we started to do was to simply take mice, inject mice with various fractions of the venom, and we would put the mouse upside down on a screen, as shown there. And if the mouse had been injected with a paralytic toxin, and so we would put the mice upside down on a screen, and if we had injected something that caused paralysis, the mice would become paralyzed, they wouldn't be able to hang on the screen, and they would fall. And so we call this the falling time. So this assay is the basis of all of our subsequent work. We simply looked at the falling time, measured it, and purified the components that caused mice to fall. And when we did this, we found that there was a straight line relationship between the falling time and the reciprocal of the dose. And in fact, the same relationship is well known in enzyme kinetics. It's called the Michaelis-Menten relationship. And so, in fact, the falling time follows Michaelis-Menten kinetics. And using this very simple assay, which I'd really like to emphasize to the high school students in the audience, you don't need sophisticated equipment to do science. This is all the equipment we had when we purified these 2 compounds. And what they ultimately turned out to be are these compounds, which are what we call peptides. So every letter here represents an amino acid, and the structure of these compounds is very similar to the structure of the proteins in our body, except that the proteins in our body have hundreds of amino acids, but these components in the venom of the snails were very short. They only had 13 amino acids in the case of this peptide and 22 amino acids in the case of this peptide. And because they were so short, we could chemically synthesize them, and we did. And when we chemically synthesized them, what we found was that this peptide behaved very much like the deadly toxin of a cobra. So when you get stung by a cobra and you die, it's because of a compound called cobra toxin that paralyzes your muscles because it prevents communication between nerve and muscle. And the component from cobra venom that kills you is a compound that attacks what's known as the nicotinic acetylcholine receptor for those with a biomedical background. The second component of this snail venom that we isolated, which was 22 amino acids, which we also could synthesize, had quite a different mode of action. And many of you in this audience know that you should never eat butete or pufferfish, because if you take pufferfish from the ocean and you're unlucky and you eat it, then you die, and you die because all of the electrical signaling in your nerves is wiped out. And the reason the electrical signaling in your nerves is wiped out is because butete, or pufferfish, have a deadly toxin called tetrodotoxin. And tetrodotoxin is a toxin that looks like a complicated alkaloid, an organic molecule. And yet the snails were making a peptide that had the same action as the pufferfish toxin, which in Japan is called fugu and is in fact eaten in Japan if the chefs are very, very well trained. If the chefs aren't so well trained, then the customers begin to drop dead. So that was our early work. Now, why do we still continue to study conotoxins? And again, this is a message that I'd like to give to the youngest members of the audience. Very often you have a goal in science, and even though you've achieved that goal, by the time you're finished achieving that goal, you realize that in fact you've stumbled on something that's far more interesting than your original goal. Okay? And this happens very, very often. So it is important when we are trying to discover what's going on in the world to keep your eyes open. Don't just be too focused. Don't just try to achieve your goals. Keep your eyes open because you might find something more interesting. And in our case, what happened was that we took the venom and we fractionated it, and we found that there were many, many components. And using the assay that we originally used, the falling time assay, only a few of these components were paralytic. But then a young student came along who just finished high school, and he got the brilliant idea that we should inject each of these components directly into the central nervous system of a mouse. And what we had been doing is we had been injecting a mouse in its body cavity, intraperitoneally. But what this kid wanted to do was to inject things directly into the central nervous system of a mouse. And I remember I wasn't so convinced that this would tell us anything, but the reason why universities are the most promising places to do research is because the students do what they want, not necessarily what their professors tell them. And that's a lesson for the faculty, I think. So what this student did was he took each of these components that showed no activity on the falling time assay, and he injected each of these components into the central nervous system of a mouse. And when he did that, he got the following astonishing result. So this is the same chromatogram with all the components of this one venom separated, and here are the paralytic fractions. But now, if you inject things directly into the central nervous system, then this one makes mice jump and twist as they're jumping. This makes mice uncoordinated. This peptide puts mice to sleep. And because we're Filipinos, we call this peptide kon antukin, okay? Because it put mice to sleep. This made them drag their back legs. This made them run around in circles. This next component made them swing their heads back and forth. This made them kick on their back and scratch. This made them depressed. This made them tremble. This made them scratch. This caused convulsions. And so what you can see is that each individual component of the venom, when injected directly into the central nervous system of a mouse, caused a different behavioral effect on a mouse. And that was totally unexpected. And so what that told us was that the venom wasn't just a few paralytic toxins, and this is only one of 4 major fractions in a single venom, okay, but was hundreds of different pharmacologically active compounds. And we could show their pharmacological activity by injecting them directly into the central nervous system of a mouse. So this one experiment changed the course of our research, because what this said was a cone snail venom was very complicated and very diverse, and therefore quite worth studying. And so we've continued to study cone snail venoms ever since. So I'd like to tell you about how the first drug was discovered from conus venoms. And again, this was the work of an undergraduate. So for a while, we had lots of undergraduates come through our lab. They could choose any cone snail they wanted. They could follow any of the activities by injecting a mouse directly into the central nervous system. And the job of all of these undergraduates was to simply purify the component that caused the effect until we could define it chemically, so then we could synthesize it and study it. So that was our plan in the early days. And so there was one student who chose this snail, which is called the magician snail, or Conus magus. And this is what this student looked like in those days. And you can tell from his haircut that this was quite some time ago. And what he decided to study was an activity that made mice shake. And he called this the shaker peptide. And he purified this peptide, and he found that this peptide, in fact, had this structure. And so we synthesized the peptide, and we were able to figure out what it did, and we called it omega conotoxin. And the reason I'm telling you this is today, this peptide is a drug for intractable pain. It has been approved both in the US and in Europe, and when one has very severe pain that is not helped by morphine, this is one of the drugs of choice. So we called it omega conotoxin, and that's not such a good name if you're going to sell things as a drug. So the company that decided to sell this compound called it Prialt, for primary alternative to morphine. And the reason this is a commercial drug, I should say that the company that developed it spent 2 or 3 years trying to improve this peptide to make it better as a drug. But in the end, they went with exactly what the snails make. They have not changed a single functional group. And so this is exactly the same as the natural product, except made synthetically, of course. Now, the reason why they got the idea that this might help in pain is because when you do binding studies in the spinal cord, you find that the peptide binds to an interesting region of the spinal cord called the dorsal horn. And the dorsal horn is where all of the pain fibers in the body come in and send a signal to the central nervous system and to the brain. And so if you have a very severe pain, the pain fibers are firing, but what this peptide does is it hits a component, a molecular component called a calcium channel. And a calcium channel is an essential component when two nerves are talking to each other, at synapses between nerves. So this is the basis for communication in the brain. An electrical signal is changed into a change in calcium concentration because calcium channels open up. And we found from the venoms of cone snails some of the first pharmacological agents that could specifically inhibit calcium channels. This particular peptide inhibits one very specific calcium channel. And in the spinal cord, that calcium channel is only present at this synapse where pain fibers synapse with a nerve cell in the spinal cord and carry the pain signal into the brain. And so if you block that calcium channel, even though you have very severe pain, you block that synapse, and so you do not perceive the pain in your higher central nervous system. And that's why this is an effective drug if you have severe